Okay, so we are going to continue a review of Maxwell's equations, and we have completed our analysis of the potential formulation, where we've utilized and we've exploited this particular Maxwell equation, that the divergence of the magnetic field is zero, and we have created the vector potential as a means of deriving the magnetic field. And likewise, we've done similar for the electric field. Now, what we have not done yet is we have not really discussed the physics notion of gauge freedom, which is sometimes called gauge symmetry. Now, I want to be careful about these two terms, gauge freedom and gauge symmetry. I prefer gauge freedom because that touches on the notion of mathematical redundancy. Gauge symmetry talks about symmetry, and symmetry is a big deal in physics, so we better be very precise about what we mean. So we'll talk about that when we get to our section on basically on gauge freedom, especially in electromagnetism. But this is a very important topic that we have to learn, and we have to, of course, get to our idea about studying Maxwell's equations in reciprocal space. In this lesson, I want to catch up with something that I dropped when I reorganized these lessons, and that is the Helmholtz decomposition. The issue of Helmholtz decomposition is very, very important. And however, it's one of those things that we just typically accept and are explained, or are taught is true and accept it. Very rarely do we go through the proof. Of course, today we are going to go through the proof. But the Helmholtz decomposition is so common out there. I've actually just shown you how I would examine it if I ran across this and said, hey, I want to hit the hyperlink on Helmholtz decomposition. I'm going to do the literal hyperlink and go right to the Wikipedia article. And I'll come down to the punchline, which is that any vector field can be split into two parts, a curl part and a gradient part. Now, we have already shown that the divergence of a curl is zero, and we've already shown that the curl of a gradient is zero. Let's see, where did we do that? We did that over here, right? We studied the divergence of a curl is zero, and we went through this analysis previously, and the curl of a gradient is zero. We went through this analysis. So the point is that any vector field, right, the key point of Helmholtz decomposition is that any vector field F can be broken down into a divergence-free part and a curl-free part. The curl-free part is called the longitudinal vector field, right? And the curl of the longitudinal vector field is zero. The divergence-free part is called the transverse portion of the vector field, and the divergence of the transverse part is equal to zero. And so any vector field that's reasonable can be broken down into this longitudinal and transverse portions. And notice that this is for the entire vector field, right? This part is true for every piece of the vector field, because remember, the vector field x is a function of x, y, and z in space, right? So the longitudinal part or the transverse part is also a function of space. So this must be true for every point in space, right? For this to be, this longitudinal part or this transverse part and this longitudinal part, these relations are true globally across the manifold that you're using, but in this case, we'll just say throughout all of space, because we're just dealing with sort of elementary relativity, where the notion of a manifold isn't so important. But we want to prove that this is the case. We want to show that this is the case, and it's worth doing because you exercise a lot of different vector calculus theorems that are worth getting to the bottom of. So the purpose of this lecture is to prove this, and that will be the goal of today. So let's begin. So an interesting thing happens when we begin. First, we push the hyperlink on this, which is basically my way of saying we open up the Wikipedia article, right? And I've clipped it and put it right in here, so we're going to go through it. And it starts with a vector function, which is a vector valued function that is a function of r, which so we can think of it as f of rx, ry, and rz, or if we want just f of x, y, and z, right? The point is it's a function of space. Every point in space has a little vector. Now, we can find the curl and we can calculate the divergence of any vector field. If you have this function, you can calculate the curl and you can calculate the divergence. So, but that's not the same, by the way, as this, right? The curl of f is not the transverse part of the f, and the divergence of f is not the longitudinal part, right? You have to find two other fields for which the gradient is the longitudinal part and the curl is the transverse part, right? That's the goal. Or I guess you should say you want to find two other vector fields for which, let's see, how would I best say that? How would we best say that? Sorry. We would best say we're looking for a vector field whose curl and a, well, you're looking for a vector field A, and you're looking for a function on the spacetime phi. And those two are bound together by this relation, in that if I take the curl of A and add it to the gradient of phi, I get f, right? And what I'm going to say is the curl of A is the transverse part of f, and the gradient of phi, or opposite the gradient of phi, is the longitudinal part of f. So that's the way to say it. You're looking for this pairing, right? They only make sense as a pair because the definition of this stuff is that it adds up to the original vector field. So I guess that's the best way to say it. All right, so we go back up here, and we say we are going to rewrite this function f using the delta function, right? And that's pretty straightforward, right? That is literally this relationship here. And at this point, understanding how the delta function works is an absolute prerequisite for QED. You've got to know this, right? This fact that this vector field is an integral over the entire volume of the function itself, basically this notion here is the convolution integral of the function with the delta function. Now notice here they say over the volume prime, right? This is kind of annoying notation, right? This should be, it's easier to understand this is dr prime cubed, right? You're integrating over the r prime variable, and you're integrating over the volume v. So I find this dv prime to be kind of annoying. I would much prefer the dv cubed prime, but we're going to have to live with it because that's what Wikipedia does. But if you land in Wikipedia to study something and you're like, what the heck? Don't move until you figure it out, right? It's totally pointless to go through this if you're puzzled over what this dv prime is all about. The dv prime is integrating over the volume, the variable. See, this doesn't really tell you what the variable of integration is. I guess that's the problem, right? The problem is that, normally you say, well, what is the integration variable? And you look right here for it, but you don't see it anywhere in here. So you have to understand that this is dr cubed. Now, what they're trying to say is you're integrating over a volume. And it's not too far afield, but it's not healthy. It's not healthy. But the problem is, okay, so now you're this far, but now what they do is they do this substitution. They take this delta function and they replace it with this object right here. And they warn you that they're going to do it up here. They say, hey, understand that the delta function can be interpreted as minus 1 over 4 pi times the Laplacian of 1 over the magnitude between r and r prime, right? That's the delta function between r and r prime. Now, we know that this is going to have that strongly peaked sense right at the point where r prime equals r, right? It's going to peak up to infinity at that point, narrow up and peak up. And, but this, do you remember this? Is this obvious to you? And it probably, well, let's just put it this way. I had to remind myself how this worked, right? So now I'm like, okay, before I'm comfortable going from this step to this step, I have got to look into this hyperlink right here. And so that's what we do now. So now we're going to put all of this on pause. The Helmholtz decomposition goes on pause for a minute, right? And we are now going to study this guy, right? What the heck is going on here with this guy. So how do we prove that this thing here actually equals this delta function? How do we prove that the right-hand side is in fact the delta function? Well, the first thing we want to show is that if you evaluate the right-hand side when r does not equal r prime, we know the delta function's got to be 0. So this guy, evaluated when r and r prime are not the same, right, has to be 0. So let's check that out. So how do we prove that this representation of the delta function is equal to 0 when r prime does not equal r? That's the first step of this process. We need to show that this thing does not equal 0 when r prime is different from r, and then we need to show that when you integrate this over a volume where r prime does equal r at some point in the volume, you get 1, right? So that's our two goals. So let's first show that this thing equals 0 when r prime does not equal r. So when r prime does not equal r, first we'll take this difference between r and r prime and we'll just give it a new name called the vector r, capital R, and it's a vector. And the magnitude of this vector capital R will be just given by the letter r. And so now our representation can be written as the minus 1 over 4 pi times the Laplacian of 1 over capital R. So this is fully equivalent to this expression here. But now that we are dealing with a vector of length r, it's going to be we're going to now shift into a spherical polar coordinate system where this vector capital R is attached to the origin. And so now we're in a nice spherical coordinate system. So we're going to write down the Laplacian in that spherical coordinate system. And all of this stuff here, this 1 over r squared d by dr of r squared d by dr of 1 over r, that is the spherical part, that is the spherical Laplacian, the radial part of the spherical Laplacian. And you don't need the azimuthal or longitudinal part, meaning the part associated with the spherical vectors theta and phi, or theta hat and phi hat. Well, actually, no, this is the Laplacian, right? So Laplacian is a scalar. So, but you don't need the pieces that are dependent, that are involving theta and phi, because 1 over r, the function that you're taking the Laplacian of, is not dependent on theta and phi. So all those parts go away. So the only thing, only this part, only this radial, I guess I'll call it the radial part, but only this piece of the spherical Laplacian does not depend on derivatives of theta and phi, because those derivatives are going to be 0. So being familiar with the Laplacian and the gradient, and for that matter, the curl and the divergence written in spherical coordinates, you should definitely be familiar with it and know how to find it, and also cylindrical coordinates, and likewise, of course, Cartesian coordinates. But don't have to have it memorized, but you definitely have to know how to dig it up. When I dug this up, by the way, and transposed it, I forgot about this 1 over r part. And doing the calculation, you'd think that'd be a disaster, right? If you forget about 1 over r as part of your spherical Laplacian, how could you possibly get the answer right? But look what happens here. You take the derivative of our function 1 over r, and you get minus 1 over r squared. Then you multiply by the r squared that lives in between these two derivatives. Remember, the Laplacian is a second derivative, and this other r squared gets squeezed in there automatically. And so here you end up with r squared over r squared. Because r is greater than 0 by stipulation, this becomes 1. The derivative 1 is 0. So this whole thing dies right away at this step. So this guy, the fact that I was missing it the first time I did this exercise in the previous version of this lecture, which I've removed, the fact that I was missing this 1 over r squared never reared its ugly head, because this thing died for a totally different reason. So this didn't have time to screw up my calculation. Yeah, this 1 over r squared definitely belongs in here, and I messed it up the first time. Anyway, the point is we've now shown that given that r greater than 0, this candidate representation of the delta function does indeed give us 0, which means if r prime is not equal to r, this guy here gives us 0. So that's good. So that's half of what we need to show. What's the other part? Well, the other part is we need to show if we take this representation of the Laplacian and we integrate it over a volume that includes the place where r prime does equal r, this better be, right? Remember, this is now the integrating the spherical, or the three-dimensional delta function, dr cubed prime, right, over some volume. This, by definition, I mean, of what the delta function is 1. So if our claim is that this guy with the included minus 1 over 4 pi, if we believe that this guy is a representation of the delta function in 3 dimensions, this integral better give us 1. So we need to calculate this integral to show that it is equal to 1. And so we proceed, right? The first thing we know is we take note of the fact that the square of the Laplacian is the square of the Laplacian. I really want to get this right. I've screwed up these lectures so many times in the past couple of weeks. The square of the Laplacian of a function in the vector calculus is equal to the divergence of the gradient of a function, right? This is a little vector calculus identity, helps you break this guy down. And it's not clear why you would do this, but usually when you take something and you create a divergence, you're setting yourself up to use the divergence theorem, and that's exactly what's going on here. So we turn that Laplacian into the divergence of a gradient. So this now is a gradient of a function. So this guy here is a vector, and you're taking the divergence of a vector. When I say a vector, I mean a vector field, right? So you're taking the divergence of a vector field, which is a function on space-time, but it's only a function of r, right? It's not a function of theta or phi in the spherical coordinate system. It's only going to be a function of what we called before capital R, right? I haven't made the substitution r minus r prime magnitude is r quite yet for this part of the proof. And take note, we've got dv prime and d cubed r prime, right? These two things, this is the same, right? This is the same. It's just, if we're going to talk about the volume integral, we want to maybe express it as a little infinitesimal volume as opposed to 3 components of an infinitesimal vector, right? It's your choice. I like to show it all here because I like to mix notation. Okay, so once we have this divergence of a gradient, what do? Well, now we execute the divergence theorem. We've got the divergence of a vector field integrated over a volume. Well, that's equal to the surface integral of the vector field projected against the area element of the surface. And this surface S has to be understood as S equals the boundary of V, where now this partial operator, which looks like a partial derivative, is notation for boundary. So S is the boundary of V. So we're hoping that we can integrate this. Well, this is just a vector field dotted into an area element. So let's break that apart. If we consider the area to be a sphere, or the volume is a spherical element, let's see, the volume is a spherical ball, and the surface area is just a straight up sphere, just the surface of that spherical ball. We now can take the area element, which is a vector, right? And it's a vector normal to the area element. That's the vector direction. And the magnitude of this little area element is the size of the area element. But I'll call that direction the normal vector, and I'll dot it into the gradient of our vector field. That takes care of this dot product. And now ds is just the element of area size, the magnitude of the area. So this is a real number now. The vector part of this, the vector nature of this has been pulled out, and we're calling it n for normal. And the magnitude nature of this, we're just leaving as ds. So that's the real number. Okay. So with that, what do we do now? Now I replace the gradient with d by dr of 1 over r, because I know in spherical polar coordinates, the radial part of the gradient is just the derivative with respect to r. That is, it becomes partial. So the gradient of f in spherical polar coordinates is the partial of f with respect to r hat, plus an angular part, a longitudinal angular part, and an azimuthal angle part. And these parts here have derivatives with respect to theta and phi. Let me get my sums correctly here. And those will be 0 because f in our case is just 1 over r, and those don't depend on theta and phi. So this is now replaces this gradient part here. We make the substitute r minus r prime equals the capital vector R, and we understand this from the definition of the spherical gradient, and we move it right there. Okay, that's not hard. And now we will take this area element and break it up, and we'll just do it in full gory detail. This part here, that equals ds, right? So ds has a d theta part and a d phi part, and it's given as r squared sine theta d theta d phi. That's just an element of area on the surface of a sphere. Definitely prerequisite knowledge to be able to go from here to here, right? It's pure spherical polar coordinates. This r squared, this r squared shows up because we're integrating over a sphere of radius r. So that's an important point too. Our spherical surface has radius r, which is why you get an r squared there. If you were just using it over unit radius, you would have a 1 there, and you wouldn't have an r squared there. And I think in the previous version of this lecture, I again confused myself by using the wrong definitions, and I did try to do this over a sphere of radius 1, which is incorrect. Well, you can do it, but it's a little more complicated. Regardless, this is the integral we now need to do. It's this double integral d theta d phi. And so when you do this, you can see right away this r squared cancels with that r squared, leaving a -1. That -1 cancels with this -1, which gives us a +1. Then I split up these integrals to 0 to pi. Remember, the longitudinal variable goes from 0 to pi of sine theta d theta, and 0 to 2 pi of d phi. And that's 1 over 4 pi times this integral of sine is minus cosine from 0 to pi. And then this integral here is clearly just 2 pi. This definite integral is clearly just 2 pi. So in other words, this guy goes here to 2 pi. This guy goes here to minus cosine from 0 to pi. And if you work all that out, these minus cosines from 0 to pi, you get minus of -1 minus -1, which ends up being 1 plus 1, which is 2. You get 2 pi. 2 times 2 pi, 4 pi, cancels, and you end up with 1. And ergo, our proof is complete. Well, it's complete except for the one possible point that we integrated over a sphere of radius 1. And it is important to note that this is true for any shape as long as it includes the point r prime equals r, right? As long as it includes the origin, I guess, when you make this variable substitution. And the reason it does is because this guy's value is 0 everywhere outside the origin. So this term here, any contribution outside the origin will be 0. So any deformation of this surface isn't going to change the integral. The entire contribution of the integral happens essentially when r prime equals r. It's a really interesting feature. I mean, that's what makes the delta function so fun and so fascinating. Okay, so that is a proof of this fact here. So now we can proceed. Okay, so now we're happy we have rewritten f in terms of the delta function. This is straight up definition. We've chosen the form of the delta function we want to use, and we drop it right into the expression for the delta function. And now we take the Laplacian and the minus 1 over 4 pi, and we pull it out of the integral. And we can do this because this Laplacian is dealing with the variable r, right? As it's written, the Laplacian is dealing with the variable r, and the integral is over r prime, right? That's yet another reason why d cubed r prime might be helpful here as opposed to dv prime, right? This dv prime it's confusing. I just straight up say it's confusing, but it is supposed to be d cubed r prime. And this, because it's derivative with respect to r, it's uninvolved in the integral, we can pull it out. And we end up with the integral of this vector function over r prime, r minus r prime. And remember, down here, this is a number. That's the magnitude of r minus r prime. Now, we can see right away that this somehow blows up into two parts. And that immediately should highlight to you, oh, we're going to deal with a vector calculus identity. And so when I see this, I know I'm not afraid of this at all, because I know somewhere out there's a vector calculus identity that takes the Laplacian of a vector. Because remember, this guy's a vector. You integrate out r prime, but you're left with a function of r, and there's nothing that kills the vector nature. There's no divergences or dot products in here. So this guy is a vector. So I know the Laplacian of some vector probably breaks down into some kind of divergence and some kind of curl of a curl. And sure enough, I remember the formula for the curl of a curl is the gradient of the divergence minus the vector Laplacian, right? And I looked that up because I don't remember it, but I look it up. Now, what's interesting is had I read through this, I would have noticed that the article actually points this out later, right? After you look at this, it says, oh, by the way, in order to understand what you've just seen, remember the vector Laplacian's a thing, right? So this is a good argument for reading through everything completely once before you start plowing through the details, because scientific papers are not always written in the very best form. Usually the stuff that's actually published is pretty good, but a lot of the stuff you'll find available on the web, written by various professors or grad students or sometimes undergraduate students write really interesting things. You know, it's not like millions of people read it and they're paranoid about every sentence being right or the structure being good. So it's always good to read the whole thing first, get a sense of it, and then go back. If I had done that, I wouldn't have had to pause everything, go back to Wikipedia, check the vector calculus section, look for the identity that I remember, which really isn't a hard one, and then realize that that's how you get from this step to this step. But anyway, this Laplacian breaks up into the gradient of a divergence, just like this piece, or I guess just like this piece, and minus the curl of a curl, which is this piece right here. So this concept gives us this, and this piece gives us that. Nice. So then what do we do? Well, once we have that, we are, what do we do next? We realize that, again, this gradient only affects the r variable, not the r prime variable. The way it's created now, it only affects r. So, but f is a function of r prime. So this gradient, this divergence here, this divergence only affects the r prime variable. Likewise, the gradient out front too, but the divergence is what we're focusing on right now. So this is basically a constant as far as this divergence is concerned, and the only piece that's not is this piece right here, the 1 over r minus r prime, right? So this divergence operator is now the divergence of just that 1 over r minus r prime. Well, what ends up actually happening is it becomes basically, as far as the function is concerned, it becomes a gradient, and the divergence piece, the only vector part here is this part f, right? This is a scalar down here. So now we just write it as f divergence and f dotted into the gradient of 1 minus r prime. And that's all because this guy doesn't affect the r prime variable, so you can move it right through the f. And likewise, that same thing is true of this curl, right? The curl becomes, the cross product part of the curl only is relevant to the r prime variable, which the differential operators don't affect because they don't affect r prime, they only affect r. So you can now move it through and you end up with the gradient of 1 over r minus r prime on both sides. And notice that this is the same. This is the same function in both places, right? And so now, then, interestingly enough, the article then says, well, let's change variables in this differential operator from r to r prime. It's a very symmetrical thing. Why not? The only thing you have to remember is you pick up this minus sign when you change variables from r prime to r prime. So that minus sign ends up here, and this plus sign ends up turning into this minus sign. So that plus goes to this minus, and this plus, the implied plus, goes to that minus. And what you're basically doing is you're taking r to r prime as far as this operator is concerned, which they explain down here as well. So now we have this lovely expression here, and we have to decide what to do next. Now, if you have some experience with this, you realize you're looking at a volume integral of a dot product, right, of a vector field with the gradient of something, and the volume integral of a cross product. So there's likely to be yet another maneuver here involving vector identities. And this time they actually alert you to it, right? They tell you this in advance. We're going to use these identities. The vector dot product with a gradient, right? A vector's dot product with a gradient is the function itself multiplied by the divergence of the vector field plus the divergence of the product of the function times the vector field, right? So we know that phi in this case, so now we check our units, right? Let's check our units. So phi is a function, it's a real function, right? Or I should write it this way. I should say phi is phi of x, y, and z. Whatever x, y, and z is, this guy is going to be a real number. So you can always multiply a vector field by a real number. That's not a problem. And you can always take the gradient of a scalar, which will give you a vector. And you can take the divergence of a vector field and you can multiply it by a real number. So all this makes sense. And likewise, all this makes sense down here, but everything ends up being a vector as opposed to a real number, right? That's a real number, that's a real number, that's a real number, and these three things are all vectors. So it's always good to really kind of check this. You might make the mistake that I once did when I first looked at this. I said, well, this must be psi of the number that's the divergence of A, right? Right? Meaning this is the argument that's being fed into psi. But that makes no sense, right? Psi is a function of space. Everything here is a function of space. So this is the product of psi times the divergence. Okay, so with those two things in mind, we can now take, what are we going to do? We're going to take, here we have a vector field dotted into the gradient of a function. So this is our function. So this guy here becomes psi, right? And this f is A, and this whole thing right here, I guess we should say, I'll erase this line here, this whole thing here, this is this psi here, and we're going to substitute all of that for this. And that's what is down here, right? The first part is minus psi times the divergence of A. So here's psi, got that minus sign in there. This is the divergence of A, because f is now A. And then you are adding to it the divergence of psi times A. So here's the divergence, and here's psi, and here's A, right? So that's the divergence of psi times A. So this part here lands right there, and this part here lands right there, right? So that's easy enough. And likewise, the exact same thing is going to happen for the curl part. That is, we're going to break this guy up using this formula here, and we're going to get psi times the curl of A minus the curl of psi times A. And that's what we have here. We have psi, here's psi times the curl of A, and then here we have the curl of psi times A. All right, so now we've traded two expressions for four, so presumably something should be easier, right? We're going up in terms. We're not making things easier. We're making things harder. But now we're going to look at now your experience should tell you, okay, there must be some simplification here, or there must be some benefit. And the benefit, of course, is that we're going to use the divergence theorem on this, because this is a divergence of a vector field, and it's integrated over all the volume. Remember, we've been playing inside the integral this whole time. Remember, all of this stuff, all of these substitutions have happened under the integral sign. So now we're going to use that integral sign, and we've done all that in order to exploit the divergence theorem for this integral, and an alternative version of the divergence theorem that I was less familiar with for this integral. So we know that the integral over the volume of a divergence is the integral over a closed surface, right? The integral over a closed surface of the normal of the vector field dotted into the normal of the surface. And that's what this is. So that's how you get from here to here, right? You make that conversion. So now you have this normal thing. And likewise, the volume integral of the curl of a vector field can also be replaced by the normal curled into the vector field. So what you get for that is you get this guy here ends up being converted into yet another surface integral. Now, if those are a little unfamiliar to you, or if you've forgotten them, you go to Wikipedia and you look. You say, okay, let's just check it out, right? Here we have a vector field dotted into a surface normal over a boundary. Well, that's equal to the volume integral of the divergence of the vector field over the volume. And here they have three integral signs over a volume. This is completely redundant, right? If you have three integral signs, you need to specify boundaries on the volume very specifically, in my opinion. Otherwise, just one will do, and you know you're integrating over a volume. It could mean nothing else, right? There's no other alternative. There's no way to interpret this other than a volume integral. Meaning, if you got rid of this, you don't lose any information. But if you were going to write this as, instead of dv, you wrote it as dx, dy, dz, right? Now, you do need three integrals, right? I don't know, am I wrong about that? It just seems like it's kind of overkill. But it does make the point that, hey, look, volume integral is like double. It's also just calling out that it's a volume integral. I guess that's fair. And likewise, the closed surface over the boundary of the normal, the vector field projected against the area. And this is presumed to be in the direction of the normal to the area. There's no other alternative in three-dimensional space. None of this works exactly this way in any higher dimension, by the way. You have to use a much more generalized version of the divergence theorem for higher dimensions. So we're going to use this one here, and I think we also use this one here. The curl of a vector field integrated over a volume is likewise the vector field curled into the the cross product of the vector field with the normal. This one, I don't think I've used this one very much in problems back in my history very much, but it is a thing. Oh, and here notice also that partial v is used for the boundary, right? So sometimes you'll see S for surface, right? So here they do use S for surface, and they're saying partial v over here. But I guess you can't do D. I guess you could do B boundary v, something like that, right? But that would probably be nutty too. So regardless, I mean, this is clear enough, right? Okay, so back to where we were. We've made these substitutions, right? We've made these substitutions, and let's see. And the next step, well, basically they're done, right? The next step is pretty trivial. All they do is take this minus 1 over 4 pi and pull it in. And what do you end up with? Well, you end up with the gradient of something, and you end up with the curl of something. And this something here is, they're going to just call it phi, right? And notice it is a real valued function, right? Because you've got this dot product killing the vector piece, and you've got this gradient, this divergence killing the vector piece. And so this piece here is a scalar function, and the gradient of a scalar function is a vector. But of course, this vector has to be the sum of two vectors, right? So that's all fine. And then likewise, you take this part here, which is a vector, and you call that A of R. And now you have F is the minus the gradient of phi plus the curl of A. And this stuff here, if this is all integrable, right? You can do these integrals, r minus r prime over the surface, that'll never be 0. And so these two things are guaranteed to exist as long as F is some kind of reasonable field, right? Everything has to be, continuous and differentiable. And then you have now just proven that F can be decomposed into its two pieces, the piece that's purely a curl and the piece that's purely a gradient. And as a reminder, this is F longitudinal and F transverse. So you've got this longitudinal and transverse decomposition of our vector field. Phew. Now, if the vector field has no transverse part, it would be a purely longitudinal field. And if the vector field had no longitudinal part, it would be purely transverse. However, arbitrary fields F can be decomposed into the two. And this will become an important point later on, but it is worth going through this, having a look at the vector identities that are important. These are all pretty important concepts. Understanding the delta function and how it works, that's a critical prerequisite concept for QED. And likewise, these divergence theorems are really good to know, because as you get into the more generalized stuff in higher dimensions, it's really fun to see how all of these can be collapsed into very, very simple statements in the language of differential forms. And so having a really good grip on these things, these here, and what is the other one I showed up here? The volume integral of the divergence is the surface integral of the normal. Actually, did that come from the same place? No, it's the same formula, essentially. But it's this formula here. But knowing all of these things in 3 dimensions is sort of like learning it the hard way, and then realizing the general form is beautifully easy. That's best done by definitely going through the system in 3 dimensions and all of its gory detail, and then appreciating the simplification that happens. The simplification is a bit of an illusion, because ultimately you do have to, whatever problem you're dealing with, you do have to sort of settle down and bang on the nuts and bolts of whatever dimensionality you're dealing with, and it can still be hard. But it's true that you cannot generalize these statements to higher dimensions, right? But they work where they need to, which is 3 dimensions in classical mechanics. Okay, so the next lesson we will begin our topic of gauge freedom, and this is all related, right? Because we're just always dealing kind of with vector identities, and gauge freedom is no exception. It's all part of that notion. And we'll cover that in our next lesson, and keep moving towards the notion of taking the Fourier transform of everything and moving into reciprocal space. So I'll see you next time.